This is the intro video for AP Calculus BC, section 4.5. We're going to be looking at integration using substitution. So this section, we're going to be looking at composite functions and how to integrate those. So to get us started off here, we're going to look at the derivative of a composite function. Let's just remind ourselves of the chain rule. ddx of f of g of x looks like this. F prime of g of x, the derivative of the outside with the inside still in there, times the derivative of the inside. Hopefully that notation makes sense. Now we're going to integrate both sides. So if I have ddx of f of g of x, that equals f prime of g of x times g prime of x, and I integrate both sides. Well, actually, before I do that, let's. I'll tell you what. I'm gonna change this up. Sorry for the little direction change here. I'm going to go ahead and multiply both sides by dx. I'm going to separate the variables. We looked at that in 4.1. So I'm going to write d of this. I'll multiply the dx over here. So now we integrate both sides. Over here, the antiderivative just undoes the differential. So we end up with f of g of x equals, well, gosh, it's like, what in the world are we supposed to do with all this? Well, remember that the equal sign means that the thing on the left and the thing on the right are equal to each other. So that must mean that the thing on the right could be made to look like the thing on the left. So here's what's actually happening. The g prime of x, if you remember from the chain rule, the g prime of x is just going back inside. It's going back to where it came from. And then we would be finding the antiderivative of f prime, and that would just be f, of course. I often use those boxes to kind of explain what's happening in here. Basically, the chain rule causes the boxes to be opened and split apart. The antiderivative here, of course, is just making them come back together. So one way of doing this is we want to learn to recognize this pattern, that the antiderivative of f prime of g of x times g prime of x equals f of g of x plus c. The key here is to make sure that the g prime of x is the correct g prime of x. So as far as using a pattern, we want to recognize f prime of g of x. We want to recognize the composite piece as well as the derivative of the inside. And we want to make sure that that derivative of the inside makes sense. We might need to make an adjustment for this. Once we've done that, we're going to apply the correct integration rule to the outside function. And if we wanted to, if we needed to, we could check our answer by doing what? The derivative. Okay, so as I mentioned, I'm going to show you a couple different ways to do this. The first way I think is very efficient and fast and accurate. It's recognizing this pattern. At the end of the video, I'll also show you what's called use substitution, which is more of a procedure, a little less intuitive, but a very good procedure for sure. So let's check out our one example here that we'll do in our video. Example number 1. The antiderivative of x squared plus 1 squared times x. So this could be done in a number of ways. I'm going to show you how to do this using a pattern. So what I'm going to do is I'm going to look at my integrand and see a couple things. My integrand, number 1, is a product, and so an integrand that's a product is an issue for sure. I look a little bit deeper and I can see that one of the factors in the product is a composite. It's x squared plus 1. It's been put into the squared function. And so I'm going to use this pattern to help me get things figured out. So I'm going to look at the inside of the composite. It's x squared plus 1. And I can ask myself, what is the derivative of the inside? The derivative of the inside, of course, would be 2x. I want the other factor to be exactly that. I look at the other factor, and the other factor is an x, which is close. It's not exactly right. Thankfully, this is something we can fix. So what I'm going to do here is I'm going to fix it. I'm going to write integral of x squared plus 1 squared, and I'm going to turn that x into a 2x. Of course, I can't just do that. I can't just change something around to my liking without balancing it out. So I multiplied that x by 2, so to balance that out, I'm going to multiply the outside by 1/2. If you remember the constant multiple rule, you can move constant multiples in and out of the integral. So really, if you think about it, what I've done here is I have multiplied the entire integral expression by just a really strategic 1. Okay, so the pattern is there. My g prime is exactly right. So what I can do is I can find the antiderivative. The 1/2 doesn't go anywhere. The 2x simply goes back where it came from. It goes back inside. And so what I then do is I anti-differentiate the outside function, which was squared. So to anti-differentiate, I'm going to use the power rule. So I add 1, and I divide by that new exponent. Make sure my plus c is in there right now. So my final antiderivative would be 1/6 x cubed plus 1 cubed plus c. So again, if you have any doubts about that, you can obviously check your answer by finding the derivative of my answer, and you'll see that it should agree with the original integrand. Okay, we're going to skip ahead a little bit on our notes and take a look at u substitution. Okay, u substitution, also known as change variable. This is really doing the same thing we just looked at. It's just doing it in a more organized fashion. So what we're going to do is use substitution. We're going to use the letter u to do so. And what we're going to do is we are going to set up the inside function to be the u. So the inside function here, when we look at our first example, is 2x minus 1. That has been put inside the square root function. I then will find the derivative, really technically the differential. The derivative of 2x minus 1 is 2. I'll just automatically multiply that dx over and I'll get 2 dx. This will start my substitution pattern. So what I'm going to do, come back over here, I'm going to replace the 2x minus 1 with a u. So I'm going to write u to the 1/2. But if I'm honest, of course, I still have the dx there. So I need to replace the dx with some expression that has a u in it. In order to do that, I'm going to divide both sides by 2 down here. That's going to give me du over 2 equals dx. And of course, if I know two quantities are equal, I can replace one with the other. So I would write this as u to the 1/2, and I'd replace the dx with du over 2. You won't see me write it that way very often. I'll typically just factor the constant multiple out right away. So I would write this as 1/2 times u to the 1/2, integral of u to the 1/2 du. Okay, so now I can finish this off. I'm going to have 1/2. The antiderivative of u to the 1/2 would be u to the 3/2 divided by 3/2. So I'm just going to automatically multiply by 2/3 plus c. This gives me 1/3 u to the 3/2 plus c. And then my final step would be to plug in the 2x minus 1 for the u. So it would be 1/3 times 2x minus 1 to the 3/2 plus c, thus completing the process. Again, if you have any questions about your answer, wondering if this works, how it works, you certainly can differentiate your answer and see if that matches up with your original integrand. Okay, we'll look at both of these sorts of examples when I see you next time.